Hello and welcome to this tutorial about STM32Cube AI Studio. STM32Cube AI Studio is a new tool for automated conversion of pre-trained AI models into C code optimized for STM32, ready to be embedded in your application. CubeAI Studio is the evolution of STM32Cube.ai in STAI product offering, and it replaces the XCubeAI plugin for STM32CubeMX. The tool supports specialized hardware, such as the ST Neural Art Accelerator, which is a neural processing unit, for example if you're using a STM32N6 microcontroller, in which case the tool generates the microcode that maps AI operations onto the NPU when possible and falls back to CPU when it's not. This page is the documentation for STM32Cube AI Studio. You can find it on the ST Wiki in Artificial Intelligence under the STM32Cube AI Studio category. Let's have a quick look together. Essentially, the tool offers a very convenient way to import a model, to convert it into optimized C code for your STM32, and then run validation either on host on your PC or on your target STM32 board. Then from there you can run code generation to have the C files associated to your model, or directly a template project that you can use in your favorite IDE. It is also important to understand the place of CubeAI Studio in the STAI ecosystem. First of all, it relies on the STAI core, which is the underlying technology, the command line interface that is used for model analysis, optimization, and validation, and also code generation, of course. Then it also uses STM32CubeMX for the project configuration and Cube Programmer for flashing your device. This is why right after you've downloaded the software from the st.com product page, you will need to go to Settings and make sure that you've installed all these dependencies: STM32CubeMX, Cube Programmer, Cube IDE or another IDE such as Kyle or IAR, and the STAI core. Also make sure that you've got the minimum required versions installed. Now let's head back to the workspace and create our first project. With me I have a STM32N6 dev kit, and what I want to do is take a model, run it for validation on the N6 target, and make sure that the model is properly mapped onto the NPU on the hardware accelerator, and also look at the memory allocations, the inference times, and so on. Then, after I'm happy with these metrics, I want to generate a project template for Cube IDE with my model C code directly integrated. So let's go ahead and do that. Create a project from scratch. I'll name it N6 Demo. I select my N6 dev kit and work with Cube IDE. First of all, I need to enable dev mode on my target, so I make sure that the boot 1 slider is to the right. I confirm that my board is connected to the PC. There's a few more options that I leave as default. Now in the target section, the neural art is activated, that's fine. It's the ST NPU. In optimization profiles, I leave everything as default, especially here this epoch controller that I keep on. Later on I will show you quickly what it looks like if I turn it off. Now in the model section, of course, I need to import a model. I don't have any with me yet, either TF-Lite or ONNX, so I will head to the STM32 Model Zoo and pick one from there. This is the STM32 Model Zoo. It's a public GitHub repo, which is very convenient because you can find lots of different models for many different use cases. I'll just pick image classification. Why not this MobileNet v2? I'll use the pre-trained on the public dataset version, and this 128 by 128 in TF-Lite format, int8 quantized. Alright. If you scroll down on the Model Zoo, you will find a link to the Model Zoo services. And this is also very interesting because you will find plenty of Python scripts. For example, looking at image classification, I will not find the models, but many scripts that enable me to run training, evaluation, quantization, and so on. So have a look, it's pretty useful. Now back in the studio, I can select my TF-Lite model here. Next section is memory pool. It's quite important. It lets you decide where you want to allocate your model's activations in RAM. So for now, I'll leave everything as default, but later on I quickly show you what it looks like on H7. Finally, validation. You can use custom data if you want to look at the accuracy of your model. For me here, I don't have any that is pre-processed, so I will just use random data and do 10 inferences. Of course, I don't want to run on host, which is on my PC, but rather on the target N6 dev kit directly. In advanced settings, there's many more things that you can tune. Please have a look at the STMicroelectronics core documentation to find more information about all that. To find this documentation, you can look for STMicroelectronics Suite, and then click See All Tools, find STMicroelectronics Core, and read documentation. Now we're ready to run. Let's go. The run might take a few minutes to complete, and STM32CubeMX might pop up a few times. Please don't interact with it. Here's what happens in the background. First, CubeMX creates a validation app to run inference on the N6 target, and STMicroelectronics Core generates the model optimized C files from the TF-Lite input. Second, CubeMX builds the project. Third, CubeProgrammer flashes the binaries to the board. And fourth, STMicroelectronics Core runs 10 model inferences on the board using random data. And finally, I will see a report with all the metrics. Now the run is finished and we have a look at the report. First, some context about the model with my MobileNet V2 with input 128 by 128 and output 1000. I have the neural art activated. And in terms of results, the inference time is about 20 milliseconds. The memory allocation was about 1.8 megabytes of flash, mainly the weights, and 240 kilobytes of RAM, mainly the activations. My model is fully compatible, which is nice. We see that there's still plenty of memory left on the dev kit. And below we have a graph with the inference time per layer and also the weights per layer. So one thing you can notice is that I only have 3 layers here. And to understand why, I need to visualize the model. On the left-hand side is the original model before modification, so it's the original TF-Lite version. And on the right-hand side, it's the model that was converted and mapped onto the NPU. So we have this EC blob, EC for epoch controller, and inside actually there's all the different layers that are properly mapped onto the hardware. So everything looks fine. And then we have 2 extra software layers. In terms of metrics, I have the cross-validation that gives a cosine similarity of 1, which is very nice. Essentially, what it means is that the results are perfectly similar between the local inference runs using the original model and the TF-Lite runtime on host, and the on-target inference runs using the optimized C model and the ST runtime. So perfect so far. At the bottom right, you have a link to open the logs. It contains the same information as the report, but also everything else that happened during the run. Now I'm ready to generate code, but before that I will quickly run a second run and keep everything the same except that I deactivate the epoch controller to show you what happens. Select the model, of course, the same one, and run. On this second report, we can notice that the execution time is slightly worse by 4 milliseconds. It is perfectly normal because we just deactivated this epoch controller, which was used to configure the processing units that are involved in the execution of the model on behalf of the MCU, but now it's off, so the MCU has a little bit more work to do itself. And now we don't have 3 layers anymore, but we have all of them. And if we look at the optimized model on the right, it doesn't have 3 layers anymore, and they're not packed together in the EC blob anymore. But they're still mapped onto the hardware, of course. So everything's fine. And we have these 2 software epochs at the very end. So pretty similar. But if you want to understand the differences between epoch controller and no epoch controller, please go to the STMicroelectronics core documentation. Here, scrolling down, you will find a very nice article about ST Neural Art NPU concepts. And from there, you find all the information about epoch controller and what it means. Back to the studio, we are ready to generate some code. So I'm heading back to my first run and I generate code. First option is to download the C model files directly, but what I want to do instead is generate a project for CubeIDE. Alright, my code was successfully generated. I can open the workspace. Here I have my .project file for CubeIDE. In this project, in Apply AI app, there's the network.c, which is a representation of the model in C, and the app xcubeai.c, which contains the entry point for initialization, AI processing, deinitialization, and so on. So now you have your project with the model integrated. You can make a few modifications and it will be ready to go. Now back to the studio, I wanted to show you a different flavor of project creation by running on H7 instead. So I will do H7 demo. I'll run on H743Zi. Select the same model as before. And here I will manually edit my memory pools. On this table we see the 5 default memory pools that are available on my H743Zi. They are ordered in terms of priority, so it means that the model's activations will be mapped onto the DTC MRAM first, then the RAM D1, then RAM D2, and so on. So for some reason, if I want to allocate in RAM D2 before RAM D1, I can just take RAM D2 and reorder it, put it before. Also, if I had some external RAM, I could add one row manually here and put the offset and the size. But this is not the case, so I remove it and save it. The run is over. We can see the inference time is a lot higher. This is normal because we don't have a NPU anymore on the H7. It's only the Cortex M7. And looking at the mempools at the bottom, we see that indeed the RAM D2 was filled before the default RAM D1. And looking at the logs, we see it here too. Finally, if we visualize the model, everything is properly optimized, but we don't have anything running on hardware accelerator anymore, which is again normal. So let's generate code and see what it looks like. Code generation was successful. I opened the CubeIDE project. Here it is. In AI, app. Again, I have the network.c. I have network data for all the model weights. And the app xcubeai.c, where you can make modifications. This concludes this introduction about STM32Cube AI Studio. As you saw, it's a very convenient tool to import models, validate them on target, and also create from scratch a basic app. There's also lots of advanced options in terms of optimization and memory management that we didn't cover today, so for that, please refer to the STAJI core documentation. Finally, if you encounter some problems or need some help, go to the ST community website, where you will find all the support you need. Thank you very much, stay tuned, and see you next time.